Okay, so we are starting limit fits and gauge design chapter. First of all, to understand need of this chapter, we will start with basic journey of any product when first from the idea generation to the manufacturing of that product. So first of all, before starting manufacturing of any product, we need to design it. So it's a task of designer to collect specifications of any product. What are the functions which are to be performed by product? That functional requirement has to be gathered. After that, for example, if we take a design of any machine component, then the type of loading coming on that component, the motions which are to be given to that component. So based on the loading condition, based on that, designer define the material first, and based on the material and its strength property, its hardness, and all material property of that selected material, based on the stress strain calculation, designer defines shape and size of product. Then same size and size are to be communicated to the manufacturer. So designer prepare drawings of those components and pass those drawings to production shop. After getting drawing on the production shop, now for manufacturing of particular product, so many operations are to be performed. We are talking about mass production. So let's take batch size of 100 components, means we need to produce same 100 components. So it's a case of mass production. So first of all, drawing is prepared and that is passed to the production shop, and so many operations are to be performed on different machines. So based on the drawing specifications, dimensions and shape of component, that operator that perform different manufacturing operations and try to achieve required shape and size. After completion of manufacturing of particular product, now the next task is to cross verifying dimension or the specification of manufactured product against drawings which are given by designer. So that task is performed in inspection department, where manufactured components, out of 100 manufactured components, some small sample of 10 or 5 components will be taken randomly, and dimensions of and the shapes of those sample, they will be checked and they will be compared against the dimensions which are given in the drawing. If they are meeting with that manufactured component dimension, they are meeting with the drawing dimensions, then those components will be accepted, otherwise they will be rejected. And then finally all those components, those selected components, they assemble together and they give final product. So this is what the entire journey of any product, from the concept to the final manufacturing. Throughout this process, so many factors which are responsible in the variation of dimensions. The first one is variation in material itself. Means if 100 cylindrical bars are to be produced, suppose, then we need to purchase raw material. Now suppose that raw material itself is having some variation in that material variation. I mean, the lot is having internal cracks, that hardness is not uniform in all the raw materials. Then due to that, you get some variation in your final product. So due to the variation in material, raw material itself, you get some variation in your final product. Second is manufacturing process limitations, because each and every process, they are having their own capability to give dimensional accuracy. If you take example of turning operation, and if you compare turning against grinding operation, then it's obvious grinding operation can give you more dimensional accuracy compared to turning. So each and every manufacturing process, they are having their own capabilities. So due to that selection of different manufacturing process, you get some dimensional variation. Next is about tool wear. As I told you, we need to produce 100 components. It's a case of mass production. Then same tool is used for manufacturing of entire batch. Then tool geometry, that will change due to wear of tool. And as tool geometry changes, then the finishing or the dimension of manufactured component is also changes. For example, first 10 components, tool geometry is different, you get different dimension. After that, tool is weared out, then you get now some variation in the dimension of next lot of manufactured product. So due to the variation in the tool geometry, due to the tool wear, you get again variation in your manufactured component. Ambient condition, in the atmospheric condition, what is the temperature of your workshop, what is the pressure condition, what is the humidity of the workshop atmosphere. Clear? So based on that, again you get some variation in manufacturing of component. For example, you are manufacturing 15 components today, where you are having temperature 35 degree, and remaining 50 components you will be producing tomorrow, and suppose the temperature you may get about 40 degrees Celsius, then due to this 5-degree difference, you again get variation in the manufactured component dimension. So that is what the example of ambient condition. Poor maintenance of machine itself, because as I told you, same component has to pass through different machines. Now one operator that maintains machine properly, but another operator is not maintaining it properly, then due to the error in machine tool itself, you get some variation in the dimensions. Now operator error and operator bias, it is about the skill level of operator itself. If operator skill is not up to the mark, then he may give more dimensional variations due to his own knowledge or its own skill level. So based on the human intervention, if more operators are involved in the manufacturing of same product, more machines are involved in the manufacturing of same product, then possibilities of dimensional variation or the error would be more, because of more person involved, more machines involved. So again, possibility of dimensional variation due to operator bias. Then after inspection process variation and shortcuts, again because this course is all about measurement, it is case of quality and inspection department. So you know about different instruments, they are having different measuring instruments, they are having their own accuracy level. If you use those instruments not with proper care, then errors in measurement would be more. So suppose by chance you are producing exact dimension, but if measurement is not proper, if measurement causes more error, then again manufactured dimension will not meet to the specification or the drawings of that product. So again, variation in dimension due to the inspection error. Assembly process variation, different approaches which you are following in the assembly of those products, again you get some variation. So these are the causes by which now we'll be able to conclude that it is not possible to manufacture component with the same dimension in the mass production. Means if you are selecting components of 100 number of components in the same batch, but again due to those factors, you always get some variation in the dimension in that entire batch. Means component to component, always you get some variation. So it is not possible to make any part precisely. It is not possible to get same dimension in more than 2 to 3 components. So that is obvious due to those factors. If by chance the part is made exactly to a given dimension, means you have manufactured component correctly as per the drawing dimensions, but suppose now if you are doing any error in your measurement, then that measured dimension will wrongly indicate error in the manufactured component. So again, component is manufactured perfect with perfect dimension, but you have not measured it properly. That's why it is not meeting with the drawing dimension. So in that way, you get some error. If attempts are made to achieve perfect size, the cost of production will increase tremendously. That's obvious, because if you want more control on the dimension, then you need to go for super finishing operations. As I told you, in case of turning, in case of grinding, if you compare dimension achieved by turning operation, by grinding operation, then grinding operation will give you more dimensional accuracy. Similarly, if you want to control more dimensional accuracy, then you need to go for finishing operations like grinding, shaving, then polishing, those type of manufacturing processes which are very costly. So indirectly, if you want more control on dimension, then manufacturing cost is also increases. So looking to this, we need to allow some variation in the dimensions, because as we have discussed, it is not possible to get exact dimensions. Always you get some variation. If you are not allowing variation, then your rejection rate would be more. So if rejection rate would be more, then production cost would be more. So looking to this obvious limitation, always there will be variation in dimension. If manufacturing variation is not there, then in case of measurement, variation would be there. And due to that, we need to allow some permissible variation in the dimensions. And that is what our today's discussion, tolerance. So next is, what is meaning of tolerance? So in simple way, we can say permissible variation from its nominal. Nominal is what we want at design stage. The designer has given some dimension to the product that we are trying to manufacture, but as we know, we will not be in position to manufacture dimension exactly as per the drawing dimension. Then we need to allow some variation, permissible variation in the manufactured component. So that is what called as a tolerance. But that permissible variation should not disturb functional requirement of product. That is again important. Clear? Because product is designed to serve some purpose. If purpose is not served, that much of dimension variation if you are allowing, then our ultimate goal is not achieved. That's why the full understanding of tolerance is amount, means the variation amount by which the job is allowed to go away from the design specifications without causing any functional trouble. It should not cause functional trouble when assembled with its matching part and put into actual service. So functional requirements should be preserved, and by considering that, you are giving some variation in the dimension. That is what called as a tolerance. Yeah. Two types of tolerances are there. One is dimension tolerance and second is geometric tolerance. So dimension tolerance is about size tolerance and geometric tolerance is about shape tolerance. So two types again in case of size, linear tolerance and angular tolerance, because some are angular features, some are linear features. So this tolerance can be specified, means how to specify these tolerances in drawing. So we can use general note or title. In title block you can mention tolerances, or it dimension itself you can mention tolerance. So that we will see later in our next discussion, how to specify tolerance in the drawing. But mainly we are having two types of tolerances, dimension tolerance and geometric tolerance. So in this course we will be discussing about only dimension tolerance, not about geometric tolerance. This term is important. Tolerance are stated in the same units as the dimension. If you are indicating dimension in mm, then variation in the dimension, which is called the tolerance, that also need to mention in same unit, mm. In mechanical engineering, generally we are using metric system, mm system. Then we need to also mention tolerance in mm. There is no separate unit for tolerance, though tolerance values are very less compared to the actual dimensions. So we are ignoring this geometric tolerancing portion, that is about shape change, but that is not part of our discussion. Okay, so some terms related to this course. One is hole and shaft. These two words will be common in our further discussion. So here you can see this is front view and this is side view of hole and shaft. So what is meaning of hole? Hole word is used for all internal features and shaft word is used for all external features. So here if you see, it's a cut section of any tube, then this hedge portion and this hedge portion, that is the cut section of the solid material. And here you can see this portion, which is called as a tolerance. And this line you can consider as the drawing dimension. Means we want this much of diameter, but as we discussed, it is not possible to get exact dimension. That's why we have allowed this much of diameter variation. Okay. Similarly, this is shaft feature. So shaft word is used for all the external features. So here you can consider one solid shaft, then outer diameter of solid shaft, that is considered as a external feature. Here you have considered tube, then internal diameter of tube, that is considered as a hole feature. And this view, that is indicating assembly of these two matting parts. So here you can see this is the tolerance zone of hole. These are the projected view. This is front view and this is side view of these two components, which are the matting components. Then this is the tolerance zone, this hedge portion, that is tolerance zone of hole, and this is the tolerance zone of shaft. So hole word is used for all internal feature and shaft word is used for all the external features. Next is about basic size or nominal size. So basic size and nominal size are the dimensions as per the design, as per the drawings. And the actual size is the size which you are getting after manufacturing. And due to tolerance, as we know, we always allow some variation in the dimension. So actual dimension will be having some difference compared to drawing dimension or the basic dimension. Okay. So actual size is the size after manufacturing of product, and nominal or basic size, that is size as per the drawing or as per the designer. Now here you can see one component. Now let us try to understand what is the internal feature and external feature, what is the hole and shaft. So if you look here, one component, this dotted portion stands for this type of internal cavity is present in this component. Then if you look here, two diameters are indicated, 550, that is the diameter of this internal step hole, step bore, which is having depth of 15 mm. And if you look this 560, then 560 is the outer diameter of this circular feature. Then 550, that is internal diameter. So 550 is called as a hole feature, and 560, that is external diameter of this cylindrical disc, then 560 is called as a shaft feature. So shaft diameter is 60 and hole diameter is 50. That is what the understanding of hole and shaft in this component. So you can see here that is mentioned 560, that is shaft diameter, which is having length is equals to 20. You can see here this length 20. Similarly, now 550 is the internal diameter and length is 15. So 550 and 15 length of this hole feature. Okay, so that is what the understanding of hole and shaft. Now here you can see 20 is the basic size, means we want this dimension is equals to 20 as per the design. But as I told you, we need to allow some variation in the dimension because we will not be in position to manufacture component with exact length 20. So here you can see 20 and we have allowed variation of plus or minus 1. So this plus or minus 1 is called as a tolerance. So 20 is the required dimension, but we are allowing 20 plus 1. So the actual dimension, manufactured dimension can be of 21 or 20 minus 1, means it could be 19 also. So we are allowing dimension variation in range of 19 mm to 21 mm. Okay, so basic size is 20, nominal size is 20, but actual dimension could be in range of 19 to 21. So this 19 to 21, that is what called as a tolerance or the variation in the dimension of manufactured component. But this variation should be such that it should not disturb its functional requirement. Okay, so mentioning the tolerance is task of designer, because designer knows actual application, actual functional requirement of product. So that is task of actually designer to define tolerance. Manufacturers, they are only following the tolerance given by designer. Okay, so I hope you understand this component and hole feature and shaft feature. Now we are moving further. Now some more terms. Here only one component is taken, hole feature is taken. So you can consider cut section of tube. So this hedge portion and this hedge portion, that is considered as a solid part of that tube, and this portion is considered as a tolerance, that variation which we are allowing. Okay, and this line is called as a basic size line, which is called as a zero line. Yeah, so this is called as a basic size and zero line. So for example, we want hole of 20 mm diameter. Okay, so basic size is called as a 20, but we are allowing dimension variation is from 21 to 22. So we want 20, but we are allowing dimension of 21 to 22. So we have offered tolerance in range of 21 to 22. So possible manufactured minimum dimension would be 21 and possible manufactured maximum dimension would be 22 as per our tolerance, because we have allowed dimension variation in range of 21 to 22. If dimension is below 21, then not accepted as per the tolerance range. If dimension above this line is 22 mm line. If dimension is above 22 mm, let's take 22.2 mm, then again that is out of our tolerance range, then that would not be accepted. So component should be only in tolerance range. So if you are manufacturing dimension with lower limit, then that is called as a minimum limit of size. So in our example, that is 21, and the maximum dimension variation is given as 22. So upper limit or the maximum limit of size is 22. So lower limit is 21 and upper limit is 22 as per our tolerance. Clear? So limits of size is actually what is the maximum permissible dimension and minimum permissible dimension. So any component that will be having two limits, one is maximum limit of size and second is minimum limit of size. So if we want 20 as a basic size, but we are allowing two dimensions, 21 to 22 mm range, then minimum limit of size is 21 and maximum limit of size is 22. If dimension between 21 to 22, then that would be accepted as per our tolerance range. So let's take one case. Suppose after manufacturing, the whole feature is having actual size 21.23. So 21.23 is above this line and below this line. So it is within tolerance range. Then that part would be accepted. Otherwise, that part would be rejected. Okay. So that is what the understanding of limit of size. So any component that will be having two limits, maximum limit and minimum limit. Dimension should not be more than maximum limit and dimension should not be less than minimum limit. That is what the condition of acceptance of any manufactured component. This is what same is indicated here for two components, whole feature and shaft feature. So again, front view, cut section of whole feature. So this is cut section of whole feature and this is cut section of shaft feature. So here in case of shaft, we allow this portion as a tolerance and this portion as a tolerance. So let's try to understand this by one example. Suppose basic size as per drawing is 20 mm. I want 20 mm. But we are allowing now some variation in the dimension of hole. Suppose let's take tolerance of 1 mm. We are allowing 1 mm tolerance. So upper limit, suppose a maximum limit for hole is I am defining as 22 mm and minimum limit for hole is I am allowing 21 mm. We want 20, but as we know, we are not able to get exact 20, so we are allowing maximum 22. If dimension is above 22, then part will not be accepted, and minimum limit 21. So here you can see this line is indicating 21 and this line is indicating 22. So how to find a tolerance then? If these two limits are given, maximum limit and minimum limit, then tolerance is simply difference between maximum limit and minimum limit. So tolerance is, so now suppose if I want to calculate tolerance for hole, then hole tolerance is equals to maximum limit minus maximum hole maximum limit minus minimum limit. So looking to above, maximum is 22 and minimum is 21. So it's obvious our tolerance is 1 mm for hole. Now let's take case of shaft, because shaft is to be inserted in this hole whenever we want to assemble this two. Whenever we want to assemble hole and shaft, we need to insert this shaft in this hole. So right now I am allowing again maximum limit for shaft is suppose 19 mm, minimum limit of shaft is suppose 18 mm. Then again, now suppose I want to calculate tolerance, means right now if you look, then this line is indicating 18 and this line is indicating 19, because maximum limit of shaft, so maximum limit of shaft is allowed as 19 mm diameter and minimum limit of shaft is allowed 18 mm diameter. So this diameter is 18. So if dimension is within 18 to 19, suppose 18.23, then that would be within this zone, then that would be accepted. But now suppose if I want to calculate what is the tolerance of shaft, then tolerance of shaft is difference between maximum limit minus minimum limit. Then it's a 19 minus 18, then we are getting again equals to 1 mm. Okay, so this is this size, this width of rectangle is 1 mm and this width of rectangle is also 1 mm. Okay, so that is, I hope you understood what is the maximum limit and minimum limit for hole and for shaft, and how to calculate tolerance and how important tolerance is in case of manufacturing of any component. So with this we are completing our today's session. If you have any query, then you can send me email. We'll try to sort it out.